Welcome to week 6 through 8, Calc 3, multivariable. We're going to be doing a few examples from chapter 14 this week in several videos that I'll be posting. Just to note, this is not a comprehensive list of concepts, objectives, or examples from the chapter. You should always refer to the chapter for more examples or notes as needed. Definitions particularly. Additional free resource is available at openstacks.org. It's a great resource, additional resource for everybody. Let's get started. So functions of serial variables. We need to find domains of function of serial variables, 2, 3 variables. Describe and draw a contour map of function with some level curves. So let's go through our first example. Find and sketch the domain of the function. We have two functions here. F of x, y equals square root of x minus 2 plus square root of y minus 1. And g of xy is equal to ln of 2 minus x divided by 1 minus x squared minus y squared. So let's go through and try to write out the solution here. So first we find the domain D. Now for the first function a, we're looking at two square root functions. So square root is only defined when x minus 2 is greater than equal to 0, and when y minus 1 has to be greater or equal to 0. So we solve for x there. We see x has to be greater than or equal to 2, y must be greater or equal to 1. So to write the domain D, it's a set of ordered pairs such that x is greater or equal to 2, or y is greater or equal to 1, where x and y are real numbers. So if we sketch the domain D on the coordinate axes, we're just looking at when x is 2, y is 1, and every value that's greater than those or equal to those. So the domain D is this infinite region over here. Of course, we can't sketch the whole thing, but it's this infinite region in the upper right quadrant here, quadrant 1, that kind of looks like half of a rectangle. Now let's go look at our second function, g. We see ln of 2 minus x, so we know with the ln function that 2 minus x has to be greater, strictly greater than 0 for it to exist. So that's negative x is greater than negative 2, so x must be less than 2. Also, we can't have this being 0 in the denominator, because if this is 0 in the denominator, then this whole thing is defined. So let's go through and find that. So it's whenever x squared plus y squared is 1. Now, we know that x squared plus y squared cannot be equal to 1, right? So this is just a circle, so in the plane. So we have to have that x is less than 2, and that x squared plus y squared is not equal to 1. So to sketch that, draw that, and dashed line because we're not including 2. And we have a dashed circle of radius 1. I'll try to draw the best I can, that we must exclude. But everything else, okay, maybe I could use red here. Everything else all these points all over here we include in our domain of g of x of y. Okay, so all of this. So that's how we would find and sketch a domain of a function in 2 variables. 3 variables is the same thing, more or less. It's just you have a z variable in there, and you would be sketching the domain in R3. Okay, so there's not too much of a difference. Here we're talking plane versus the space curve. Okay, so let's jump into next example. Draw a contour map of a function showing several level curves. So we have 2 functions, f of xy equals xy, f of xy equals ln of x squared plus 4xy squared. Let's take a look at this first one. So whenever you're drawing level curves, you just want to let the function be a constant. Typically, in many books, they let it be c or k. It depends what you want to use as your letter, but in the end, it doesn't really matter. So let's let xy be equal to k, where k is constant. And then you can let k be anything. Now, if you let k be 0, then x or y is 0. It's not very exciting. So let's k be 1, for example. So if k is 1, then we have xy is equal to 1, or y is equal to 1 over x. And that's a pretty common function. So we know we can draw that. That's pretty straightforward. I'll just sketch that here. That when k is equal to 1, you get 1 over x as your level curve of your function. So you let k be 2 to get another level curve. And the only difference will be that y is equal to 2 over x, right? It's the same computation, just 2 over x. So you're just multiplying everything by 2, so everything will just become greater or less depending upon the quadrant that you're in, right? So k is equal to 2. And you can keep on going the same way. K is equal to 3. It would kind of look like this. This is just a sketch. So this would be the level curves of this. Basically what you're doing is you're slicing the function, right? Horizontally slicing the function when k is 1, k is 2, k is 3, etc., 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 and then drawing that on your 2D plane. And then same thing with this. Okay, this function ln of x squared plus y squared plus 4y squared. You just take that and set that equal to k. And you can let k be, let's just simplicity, maybe 1 and 2. So if it's 1, then we know that this is true. And of course, if that's true, then you have 4y squared is equal to e to the first power, right? And then this looks very familiar to us. If you divide everything by e, then you get x squared over e plus 4y squared over e is 1. And you want to maybe write that as, something a little bit nicer. That's y squared divided by e over 4 equals 1. This should remind you of a conic, right? And more specifically, it should remind you of an ellipse. So this goes back to our conics. And we can draw this as root e minus root e here, plus root e over here. And e over 4, square root of e over 4. I'm just going to make this up for estimation purposes e over 4 and minus square root e divided by 4. And anyway, it'll look something like that, and that's where k is 1. And of course, if k is 2, the only difference would be that this ellipse will get a little larger. So you do the same calculation, essentially, and you get quite a little bit larger ellipse, okay, when k is 2. And those are the level curves of this function, is that you just keep on graphing k is 1, k is 2, k is 3, and then on your 2D plane, and then you get the level curves. Let's move on to important concepts, limits and continuity next. These you'll want to have the textbook in front of you and just to view the definitions of the limits and especially continuity. Although I'm going to use some of the definitions, you should have that also in front of you as you watch this next section. It'd be probably very helpful for you. So, limits and continuity. So, formal definition of limit of a function in 2 or 3 variables. Computing limits of functions of several variables using paths and the formal definition. Definition of continuity of a function in 2 variables. So these are just some important points that you'll want to keep in mind when moving through this section. So let's see this first example. Let's find the limit if it exists, or show the limit does not exist. So we have this limit here, xy approaches to 0, 0, x to the 4th minus 4y squared divided by x squared plus 2y squared. Okay, so one of the things you want to notice here is that you might be tempted just to plug in 0, 0. That's a natural reaction. If I plug in 0, 0 here, I'll get 0 divided by 0, which we all know is undefined. Or if you're thinking back in calculus, you had 0 over 0, that would be called in your limit a indeterminate form, okay? So here we can't just plug in 0, 0 because of these reasons. But what we can do is we can choose a path, okay, and evaluate the function along the path. And if we find that if the limit along 2 different paths that we take are different, then the limit might not exist. Alternatively, if they do coincide, then the limit could exist. So let's choose a limit here. Let's choose this path. So I'm letting y be 0. So if y is 0, then you have just x to the 4 divided by x squared, which we all know that is just x squared. And the limit of x squared as x goes to 0 is just 0. Right? This is provided, we can do this cancellation provided that x is not 0. But this approaches 0 in the limit. Okay. So that just shows that this is 0. Now let's check another path. Let's let the x be 0 this time and let the y vary. So we see that we get negative 4y squared over 2y squared, and again y can't be 0 for this next cancellation. And we see that the limit as 0y approaches 0, 0 of negative 2, that's just of a constant, so that's just negative 2. Here we chose 2 different paths, but we arrived at 2 different values of the limit. So this shows that 0 is not equal to -2, and so the limit will not exist or does not exist, D and E, because we chose two different paths and we arrived at two different values in the limit. So this is why the limit does not exist in this case. This is not using the definition, although using the definition would be very tedious in this example. There are some examples in your textbook, for example, that where you would use the limit and it wouldn't be too tedious to do so. But we'll get to that in perhaps the next example where we use the definition of the limit to actually show whether the limit exists or not. So that's this limit. Let's look at this one. xy, a limit is xy goes to 0, 0, xy to the fourth divided by x to the fourth plus y to the fourth. We have to show if it exists, does not exist. And here we're going to be using the definition to change it up a little bit. Okay, so to change it up, I'll use the definition of the limit to show that it exists or does not exist. So we'll use the definition. Use the definition of the limit. You don't need to. It's just that I'm doing this for the purposes of this example, right? One thing you'll notice about this example is it falls in the same case as the last example, where that if you put in 0, 0 for x and y, we get 0 over 0 again, which is called an indeterminate form. The limit does not exist there, so you can't just plug in 0, 0 for x, y in this example. Okay, so you can't just plug this 0, 0 into this. So let's use the definition. What does our intuition say before we go ahead and use the definition? Our intuition says that this limit might be 0, right? Because we see that y to the fourth here, okay, if you plug in a value there, if you take partial derivatives, although we haven't learned too much about that yet, we can see that it could approach 0. All right, so in our limit, okay, we probably should be thinking that this is going to be approaching 0, but so our guess is that I'll just say we suspect that this approaches 0. So let's look at our proof using epsilon delta proof. Okay. So we let epsilon be greater than 0. Want to find a delta greater than 0 such that if this is using the definition of the limit, by the way, square root of x squared plus y squared is less than delta, then absolute value of our function minus the limit value is less than epsilon. So basically what this is saying, this is implying that if is less than delta, then to summarize, is less than epsilon. We can do that because square root function is always going to be positive. If x and y are non-zero, both non-zero, then it's always going to be positive, so we can eliminate the 0 on the left-hand side of this delta here. And we can also take the absolute value of each component here of this fraction, and x to the fourth, y to the fourth is always positive. Y to the fourth itself is positive for any y value that you choose, so the only one that gets the absolute value would be the x, okay? So that's how we can kind of break this down a little bit further. All right, so what we see here then is that this here, this fraction, will always be less than or equal to the absolute value of x. Why is that true? It's because if we have y to the fourth divided by x to the fourth plus y to the fourth, that fraction, okay, this fraction right here is always as y, let's say some value, and x could be any value. Okay, this is going to be 1 or less. Okay, so when you multiply this by 1 or less, then it's always going to be less than or equal to absolute value of x. Okay, so there's the reasoning for that. Now that's equal to square root of x squared. All right, that's for any x value that we can choose. Okay, of course it has to be positive here in this case, which is always going to be less than or equal to square root of x squared plus y squared, right? So if we just let delta be equal to epsilon, okay, we see that, and I'm running out of a little space down here, but we see that this guy is less than or equal to this, which we knew from the beginning that that's less than delta, which we just let equal to be epsilon. So there we found delta. If we let delta be equal to epsilon in this case, then we've satisfied the definition of the limit. So, and this limit approaches to 0. All right, so this is the way that we would use the definition of the limit to solve a limit problem. It's a epsilon delta definitional limit. Extremely similar to the Calc 1 version of the limit, except now we're in Calc 3, and we're dealing in 3 dimensions instead of just the plane. So, but it's very similar.